Welcome to 16.4. 16.4, we're going to parameterize surfaces. We're also going to talk about computing surface areas and surface integrals. So our goals for today, we're going to talk about how to construct parametric equations of surfaces. We're also going to compute and describe some tools that we need to be able to describe surface area. These tools are our tangent vector in the u direction, our tangent vector in the v direction, and a normal vector. And then finally, we're going to compute some surface areas and surface integrals using these parametric equations of surfaces. So as a start, let's start with a review. We've seen parametric equations before in the context of a line. So let's say that we have, so I'll say recall. We have a line with direction, I'll call D, and so that's going to be D1, D2, D3. It has a three-component vector. That's the direction it's in. And let's say that the line also has some point, and we're going to call the point A, B, C. That's the point that goes through this line. And we constructed equations for these lines. Typically we called them L of t, and it would be equal to, just like point slope form, it's the point ABC plus t times, I should actually be meticulous and represent these as vector outputs. I always, I flip-flop those a little bit, and I apologize. So we have our point ABC, our initial position, essentially. We could think of it sort of as our t-intercept when t equals 0. And then our direction vector, d1, d2, d3, multiplied by t. Because that means that we start at our point ABC, and we can stretch and shrink our t vector out in whatever direction we want to be able to trace out the line in this direction d. I'm going to point out that we can simplify this a little bit. I don't know if you'll call it simplifying, but if I distribute this through and do some addition, I could think of the first component of my line as being a plus t d1, just by adding the first components, and then the second component would be b plus t d2, and the third component is 3c plus t d3, where I'm thinking of this equation for my x component, this equation for my y component, and this equation for my z component. The reason why I want to point this out is because this is exactly analogous to what happens when we talk about parametrizing surfaces. So by definition, our parametrized surface, typically we represent with a capital Phi. I'm not sure why we have some capital Phi. And instead of, so in the last example, our line was parameterized just by one parameter, t, and it gave us a one-dimensional thing. It gave us a line. Now we're going to consider parameterizations with two input variables. And our outputs in this case are going to be, it's going to be a vector in R3. So it's going to have three component functions. A component function that's a variable of uv in the x, a variable of uv in the y, and with variables uv in the z. So notice that my inputs, I have two different inputs, u's and v's. I could think of these as points in R2. And the outputs that I get are a set of vectors, which are outputs in R3. Let's see a quick example of something that looks like this. Let's say that I have a plane. A plane is a type of surface. A surface is something that's of two dimensions that's out in three-dimensional space. So let's say I have the plane 3x plus 2y minus z equals 4. And instead of writing it in terms of x, y's, and z's, I want to be able to write it as a parametric form. Why? It's sort of for the sake of illustration, because planes we already know how to work with like this, and there are other shapes that we don't know how to work with as easily. So considering this plane, how would I be able to parameterize this? I need to come up with a u and a v variable and I need to be able to represent each of the components as u and v variables. I'll show you my trick. This is a magic trick. Magic trick. Maybe it's not that magic. But if it's ever the case that I can set z, or any of the other variables, as a function of x and y, then it means that my parametric surface can be parametrized really, really easily. So let's go ahead and solve for z. And we see that when we solve for z, we can get that z is equal to 3x plus 2y minus 4. So the magic trick is, when I have to decide what my u's and v's are equal to, I'm going to make it as easy as possible. And I'm just going to set my u exactly equal to x and my v exactly equal to y, because then I know that my z in this case, maybe I should flip-flop the order, but my z is equal to 3 times x, which we're calling u, plus 2 times y, which we're calling v, minus 4. And it means that I can use these 3 equations as the equations that go into my parametric function. So in this case, my parametric function for this plane, the first component function, we're saying that x is just the boring function u, y is the boring function v, and z is the boring function 3u plus 2v minus 4. Okay, Carolyn, that was a lot of work, and we aren't quite sure what the payoff is just yet. This sort of looks like something that would be more complicated than what we started with before. Let's see another example. So for our next example, let's consider this cone. Let's consider the cone where z squared is equal to x squared plus y squared. Alternately, I only want the positive part of it, so I could rewrite it like this. Z is equal to the square root of x squared plus y squared. How do we want to parameterize this? Well, we can do the same magic trick that we did before. I'm going to let my x be equal to u, my y be equal to v, and in that case it means that my z is just going to be equal to the square root of u squared plus v squared, and it means that my final parameterization of this, phi of uv, is going to be equal to my x component function, which is just u, my y component function, which is just v, and my z component function, which is the square root of u squared plus v squared. And that's that. However, if I actually want to deal with this function, this is messy to integrate, this is hard to deal with, so instead of leaving it like this, I'm going to give us an alternate parameterization. We're going to think of this somehow differently. For my alternate parameterization, instead of assigning my u's and v's exactly to my x and my y values, I'm going to assign them to things that you might think are a little crazy. I'm going to decide I want my u's to be equal to this radius value. And I'm going to let my v's be equal to theta, just like we would in cylindrical coordinates. So these are the things that I'm thinking in my head. I still have to translate these things in terms of x, y's, and z's. So when setting up my phi function in this case, I still am looking for a way to express my x value in terms of u's and v's. So if I pick a random point on this cone, I need to be able to tell what is the x value at that point, right? And it turns out that that x value, just by the geometry of this, I project this down, whatever this x value is. Maybe you don't like this picture, but I claim that the x value in this case is going to correspond exactly to r times the cosine of theta. And that's exactly because we're using our assignment to be consistent with our cylindrical coordinate system. So in this case, it means that because our x-coordinate is r cosine theta, and I'm letting my r be equal to u, my x component function is going to be u cosine of v. Similarly, my y component function is going to be u sine of v. And the reason why this is sort of nice is the fact that now I don't have to have my z in terms of square roots. In this case, because of this very particular cone that we chose, we know that x squared plus y squared is r squared, and so z is exactly equal to r. Another way that we can do that is just to assess visually. We know that this slope of the cone is exactly equal to 1. So if my r is equal to 1, my z, this height right here, would also be equal to 1. That my heights are equal to the radiuses. Whoops! And in this case, we're letting u represent r. So I'm pointing out that this is an alternate way to parameterize this particular cone. And it's a parametrization that now might allow us to be able to do integrals a little more easily than if we had square roots trapped up in